Dear all, thank you for attending this presentation. My name is Tan Shan. In this presentation, I'm going to be presenting MultiTask federated learning for traffic prediction and its application to road planning. So it is joint work between researchers from Mitsubishi Electrical Research Laboratories and the researchers from Virginia Tech. A quick overview of this presentation. First, I will give you some background information and the motivations why we do this specific work. Next, I will present the system model, which includes multi-horizon traffic speed prediction model and the road planning problem. Next, I will introduce MultiTask federated learning framework for the speed prediction and also give the solutions to the road planning problem. Finally, I will introduce simulation results and some conclusions for this specific work. So without further ado, let me start with the basic background and the motivation. So as we all know, having accurate speed predictions are very important because it can mitigate the traffic congestions. The reason is that with the speed prediction, the driver can make actions to avoid, for example, congestions. And in that case, it can increase the fuel efficiency because there are going to be less fuel vehicles stuck in the congestions. And also it can alleviate the air pollution. And one of the reasons why there were so many papers working in this specific traffic speed prediction is that with the wide use of the sensors and devices, for example, the rope detector, the toll station, the cameras, we have more and more traffic data available that we can use for the traffic prediction. And there are two major approaches for the traffic prediction. The first one is a parametrical approach, such as the autoregressive integrated moving average model and the common filtering model. But those kind of approach can only handle traffic with regular variations. For example, recurrent traffic congestions in morning and evening rush hours. But when it bumps into some abrupt traffic, for example, a crash, it cannot handle those kind of scenario very perfectly. The second approach is that we can use machine learning model like long short-term memory and the convolutional neural network to do the prediction. But there are some challenges when implementing those kind of approach. The first challenge is that most of those kind of machine learning models are targeting a single task learning model. And as we all know, the traffic data is very diverse, it's very complex. Having a single task learning model may not be perfectly predict the traffic data across different traffic scenarios. And also when the traffic sensor relying upon its own data to do the prediction, it will bump into another issue, which is the insufficient training data needed by the limited on-chip memory. To solve that, you can definitely share the data to a centralized unit, but it will lead to another issue, which is privacy concern, because some traffic data will actually include some privacy sensitive information, for example, the license plate, and also it will coupled with the huge communication cost between the traffic sensors and the centralized unit. So to solve those challenges, so in this work we propose a novel multitask federated learning framework where we have divisive hierarchy clustering to identify different traffic patterns. And we also use federated learning to collaboratively train the different models among different stations without sharing the actual data. And also we implement the multi-horizon speed prediction from the multi-task federated learning framework into the real problem, which is the road planning, where we have the modified A-star algorithm to solve those kind of problems. And we also use the real data into the simulation to verify that our proposed approach is effective. So before I dive into the solution, let me first introduce the system model. Here we have the multi-horizon traffic speed prediction model. So for the prediction model, we have the data where we basically input and output a pair. So for the input, basically just history data. And here we have L, which basically represents how much history data we consider within the input. And for the output, we have the actual output measured by the sensors, and we also have the output predicted by the machine learning model. So H over here basically represents how many horizons we consider in the prediction. And for each traffic station, it targets to find the machine learning model omega to minimize the loss. And SN over here basically is the total training loss, total training samples. F basically is the loss function. And the second part for the system model is the road planning problem. So after we have the multi-horizon speed prediction, we can actually decompose the long road segment with multiple traffic stations into small sub-segments where each sub-segment has its own station. So here we have VI to VK, which has two traffic stations. And in that case, we can decompose the long segment into two sub-segments. So in particular, VI to VJ, and this specific speed is measured by this this station. And for the second sub-segment from VJ to VK, and its traffic is measured by this specific traffic station. Similarly, based upon the results we have, we can build a time-dependent graph. We have the vertex just include the intersection and the connecting point. And also we have the edge set, which includes the row subsegments. And we have the weight. And the weight basically is calculated by the length divided by the predicted speed. And it's a time variant because we have the multi-horizon traffic speed. So at the end of the day, we have the road planning problem where we basically determine the road leaving the current location to the destination point with the least traveling time. And most of the algorithm targeting to solve the road planning prediction problem focus on the static graph where the weight is fixed over time. But in our case, we kind of change it all the time. So we need to come up with a new solution to tackle the road planning problem in the time-dependent graph. So to solve the first problem in terms of traffic speed prediction, we propose MultiTask federated learning framework. So in this specific framework, there are two steps. So first, we have divisive clustering method where we partition the data into different types. So here we have the raw data. We have so after the clustering method, we have different clusters, where different cluster represents a unique traffic pattern within the traffic data. And the criteria that we used in the clustering can include weather condition, time, special events. And the second step within the framework is basically we run the federated learning. And the federated learning is in essence is a multi-communication round between the server and the traffic station. And each communication round, the traffic server basically sends the global model to all stations. And each station will train the received model on its own data and send its updated model to the traffic server. And the traffic server will aggregate the received model and generate a new model. So those kind of steps will be repeated between the server and the station. So as the communication round proceeds, the stations will converge to using the same optimal learning model. So that's a key idea in terms of the multitask federated learning, and you can find more details within the paper. So after we have the traffic speed prediction, we can solve the road planning problem by using our modified A-star searching algorithm over here. So there are four major steps within the modified A-star searching algorithm. The first one is that we assign infinity to all nodes within the time-dependent graph at the associated time, except the starting node at 0. So here, V1 is 0, and for other nodes, it's infinity. And next, we find the adjacent node to the starting node, and we compare the assigned associated time with a specific variable. And that specific variable is calculated by adding the arriving time from the starting node to the adjacent node and the expected traveling time from the adjacent node to the destination node. And that specific traveling time is a heuristic and is calculated by the Euclidean distance over the maximum speed. And we compare those two variables, which is assigned associated time with the variable that we just calculated. And we find the minimum value. We updated the associated time for the adjacent node. And the third step, we among all those adjacent nodes, we find the one with the minimum associated time. So here, since we only have one option, which is V2, so we just keep V2. and we repeat the steps 2 and 3 for all the adjacent node for this specific node. So here we just repeat the steps 2 and 3 for node V3 and V5. So we just repeat those steps until we arrive the destination node, and then we can just obtain the path for the optimal route with the least traveling time. Note that because we can set time dependent graph, the traveling time for each edge is kind of changing over time. So here in the next section, I'm going to present some information in terms of the simulation. So we can see the real data from the California Department of Transportation, and we use the data specifically from San Jose area and the Los Angeles area. And we use 2 layers of LSTM, and each layer has 64 neurons, and we use TensorFlow as our training platform. And for this specific slide, we highlight why we use the MultiTask federated learning. And we have 2 baselines. The first one is single task federated learning, where there is no divisive clustering, and the second one is traditional single task machine learning, where there is no federated learning, no divisive clustering. And we can see three time ranges for the multi-horizon: 5 minutes, 30 minutes, and 60 minutes. So as we can see from the table, the multitask federated learning can achieve much accurate results compared with other 2 baselines. And for this slide, we basically verify that our multitask federated learning can achieve optimal learning model for different traffic scenarios. So as we can see, when the communication around process, the loss function for different traffic scenarios is decreasing. So basically, you can verify that the effectiveness of our proposed multitask federated learning framework. And for this slide, we verified that our proposed A-star algorithm. So here we have 2 baselines. The first one is a Google Map-like scheme, where the road planning decision is determined by the road map and the current traffic information without any traffic speed prediction. And the second one is a distance-based scheme, where only road map information is considered within the road planning steps. So that's a basic map for the San Jose area, where we have 2 nodes, node A and node B. And we select those 2 nodes on purpose so that all those 3 schemes are choose the same steps over time. So here we have the prediction and actual traveling time prediction for all those 3 schemes. And we calculate the difference between the prediction value and actual value for all those 3 schemes. So as we can see from this figure, our proposed scheme can achieve much accurate traveling time prediction for the path, unlike other 2 baselines. And we can observe similar results for the Los Angeles area. So because of the time issue, I'm not gonna represent the results for Los Angeles area over here, and the conclusions. But I can show you the conclusions for the Los Angeles area. So basically, it can verify that our approach can achieve much better route selection with a lower traveling time estimation. So to conclude this work, we developed a novel multitask federated learning framework for the traffic prediction, and we use multitask federated learning framework to solve the real problem, which is route planning. And we propose a modified A-star algorithm, and we use real data to verify that our proposed approach can achieve much accurate traveling time estimation, and we can achieve effective route selection. And that's all. So if you have any questions, you can send your questions to this email address, and I will be happy to address all of your questions or comments. So thank you so much.